Next section is on nuclear chemistry. So radioactivity. So atoms that are unstable. So if an atom is radioactive, it means it's unstable. And actually the word radioactive means it used to, they emit, among other things, radio waves, but of course it's much, much more than just radio waves. That was the original idea of radioactive, but there's other rays. We'll talk about this in the future. The uronic waves would turn out to be gamma rays. But radioactive, among other things, like I said, it's unstable. There's lots of applications for radioactivity, especially in medicine, for diagnostics and various things. There's also, we can use it for dating, so things like rocks, but also for things that used to be alive with carbon dating, and also led to nuclear fission, which we can use for nuclear power and also for weapons as well. And an unfortunate part of radioactivity, one of the major applications, of course, is weaponry. So radioactivity was discovered by Becquerel, and he was studying if phosphorescent materials also gave X-rays, because X-rays you could see them as they can expose certain photographic plates. Phosphorescence is it's a glow in the dark. So glow in the dark, it's long emission of light. And Becquerel noticed a few things, that a lot of these minerals had uranium in them, and the mineral was not exposed to outside energy. So he named them uranic waves. And they're kind of like X-rays, but they're gamma rays, basically. And Marie Curie came along. Wonderful, amazing scientist. Marie Curie won the Nobel Prize twice, and then her daughter won it as well. But she isolated radium, and it glows kind of a light green color. And they used it to make watches. So maybe you can look at the Radium Girls. They're the people that painted the watches, and they all got really sick from the radium. But that's a different story if you want to check that out. Radium watches are scary. You could see them with your eyes closed, even because of the beta radiation that the radium put off. She also found polonium and named it after Poland. So polonium, of course, is a very, very toxic element. And so interesting that she picked one that was just horribly toxic. Unfortunately, Marie and her husband Pierre, they got very sick from all of the radiation that they worked with. So, Pierre died, had an untimely death, and but Marie, she obviously had children, but she, you can read about her. She's got an interesting life, let's just say. So interesting life, wonderful scientist. And let's talk about radiation. As hopefully as a review, the number of protons defines an element, and the number of protons is the atomic number. And an element can have different number of neutrons, so same number of protons. Protons define the element, but different number of neutrons. Those are called isotopes. And the isotopes are defined by their mass number. It's the number of protons plus the number of neutrons. So when you have a chemical symbol, even the atomic number and the chemical symbol are actually redundant for each other, but sometimes the atomic number then is not included, but the mass number is the top number. So you can use just something like, and you can say something like oxygen 16. So that way, and then you automatically know that since oxygen has 8 protons, because oxygen has atomic number 8. So some important symbols, atomic symbols, are right here. And you can have both the nuclear symbol and the atomic symbol. So how many protons and neutrons are in the isotope, or aluminum-27? So the bottom number, aluminum, is the atomic number. It means there's 13 protons. And then the number of neutrons is the top number minus the bottom number. So it's 27 minus 13, or 14 neutrons. Types of radioactive decay. So first of them is alpha particles, alpha rays. These are helium nuclei. And so alpha rays are the least dangerous of the radioactive, radiation, provided it's outside of your body. So alpha emitters are horribly damaging inside your body because it's like a pinball. So when you have that alpha particle, it's really massive, and it's a pew, 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 goes around your body and causes massive damage inside your body. But outside of your body is not that much of a danger. Beta, they're not too bad. It's a high energy electron, and these can cause certain it can cause cataracts. A lot of beta rays can cause cataracts. They're mostly harmless. They tend not to go very far. One thing with beta rays, though, be careful with them around metal, because beta rays will bend around metal and emit X-rays, which are also dangerous. So that's one thing with the beta emitter. Gamma rays, this is just plain old electromagnetic radiation, but really high energy photons. And these can cause damage, and they're very hard to stop. They go through just about anything. So some unstable nuclei emit positrons. So that's the antimatter for electrons. Matter is the same thing as antimatter, except for the handedness of spin and the charge. So, and when antimatter and matter meet each other, they turn into energy. So emitting a positron is going to emit a gamma ray. So it's when positron meets an electron, it turns into a gamma ray. So essentially, positron emitters also are gamma emitters because the positrons are destroyed. I mean, they annihilate, the matter and antimatter annihilate each other and turn into energy. And some nuclei also undergo electron capture. Sometimes you might see it as K capture. That's a leftover from German. So the K capture, electron capture, Kern capture, that just means the same thing. That's just all the electron capture, where an electron is pulled into the nucleus and it turns a proton into a neutron, is what happens. So the nuclear equations, the top numbers have to be equivalent, equal on both sides of the equation. The bottom numbers have to be equal on both sides of the equation. It's like the reactant is also known as the parent nucleotide or nucleide, and the product is known as the daughter nucleide. So we always just have daughters in the world of nuclear chemistry. So every single product is a daughter. And notice that the top numbers on this equation, the uranium-238 turns into thorium-234 and an alpha particle. Then the top numbers, 238 equals 234 plus 4, and 92 equals 90 plus 2. So the top numbers and the bottom numbers are equal on both sides of the equation. So alpha decay, the atomic number decreases by 2 and the mass number decreases by 4. It's the stable helium nucleus. And this is also a large source of the helium on planet Earth. So from the alpha decay of things like uranium and thorium, the uranium-thorium cycle releases alpha emitters, which essentially turns it into helium. So if you wonder where the helium in the Earth comes from, it's from this. So alpha decay, and you can see they have the helium nucleus. And this is interesting if you go through the kinetics of it. It's actually a quantum mechanical tunneling is what causes the alpha emitter. So it's an interesting thing if you study the quantum mechanics of this further. So ionizing power, what does ionizing mean? Ionizing means to rip off to create ions, in this case ripping off electrons. And Alpha radiation has the highest ionizing power. It's the most massive, and it can cause quite a bit of damage, but it doesn't penetrate very far. So alpha emitters, as I mentioned before, are pretty safe outside the body. Inside the body, they're horrible. You do not want to have an alpha emitter inside the body. Beta decay, it's more penetrating than alpha, but it's not too bad. Beta particles also increase the atomic number by 1. So this is when a neutron turns into a proton and an electron. And so the mass number stays the same, but the atomic number increases by 1. And beta decay, so a neutron becomes a proton. And a free neutron will beta decay by itself. So free neutrons are not very stable. Gamma rays, these are high energy photons, so it's this is a way for a nucleus to cool off. So you can get a high energy excited nucleus. So just like what you learned of electrons. So same thing with electrons, same thing with protons and neutrons. Protons and neutrons have energy levels. They also have the Pauli exclusion principle, just like electrons. The difference is the energy levels between protons and neutrons are very large. And whereas electrons are pretty close and they can interfere with each other. And but the thing with the protons and neutrons, the energy levels are so far apart, they do not interfere with each other at all. They're standalone. So it makes the math actually a lot easier if you delve into the quantum mechanics of nuclear chemistry, nuclear physics. It's easier than regular chemistry because it's just the energy levels are so massive and the differences are so massive that it doesn't really matter about any sort of wave patterns. But they have the same thing, p orbitals, s orbitals, d orbitals. It goes really high though. And when you have protons and neutrons in excited states, same thing with electrons, they relax down, whereas electrons emit visible light, nuclei emit gamma rays. And it's these photons, the gamma rays, are very powerful. And they ionize just about anything. Well, they're going to ionize any electron that it hits. So if we have in the next door, we have an alpha, a beta, and a gamma emitter. Which are you most likely to detect? And it's the gamma ray. Another thing, though, whenever you have an alpha or beta emitter, there's a gamma ray too. So they don't. You're not just going to have an alpha emitter, not a gamma emitter. Everything is going to be a gamma emitter. So showing the picture, alpha is stopped pretty easily. Beta stopped moderately easily. Gamma, though, it's really hard to stop a gamma ray. Positron emission. Positron has a charge. It's the anti-electron. It's a positive electron. And it's similar to beta particle, of course, but it's going to positrons though they're going to seek out an electron and then they're going to annihilate that electron and it's going to annihilate itself and the electron have a gamma ray. So positrons also mean gamma rays. So later on we'll learn about PET scans. PET scans use positrons to image certain things like brains, and the reaction though is from a proton turns into a neutron. And so here is an example of when carbon-10 turns into boron-10, and a positron is emitted. And electron capture. So this means an electron is ripped into the nucleus, and it's a similar effect, but it's a different process. The similar effect as a positron emission, but because it involves a proton turning into a neutron, but it's a little different. So, for instance, ruthenium here turning in Kern capture. Using K capture. Using the old, I don't think I'm that old, but I'm using the old school terminology to electron capture to make technetium there. And technetium is a man-made element, by the way. This would be a very unstable. Well, I guess technetium is very unstable in general. Technetium is not a very stable element at all. It's very radioactive. So here is an image to show the different decay modes that I've already mentioned there. And remember that the parent is on the left and the products are the daughters. So we have the daughters. And and remember the rules of the nuclear equations. So what causes radioactivity? So the four fundamental forces, if you recall, are gravity, nuclear strong, nuclear weak, and electrostatic. So I guess I didn't list them in order. I guess gravity is 1, electrostatic is 2, nuclear strong is 3, and nuclear weak is 4. So gravity is the ever-positive force that matter exhibits, deals with the deformation of space-time. Electrostatic, that is, deals with electronic and magnetic fields. And nuclear strong, this is a force that is felt by protons and neutrons. Some other particles feel it as well. So pions, for instance, can feel them. But for this class, let's focus on protons and neutrons. Now, the idea of the strong force is that you have a nucleus that has a bunch of protons. Protons are positively charged. They want to repel. So you have to have a force that's stronger than the electrostatic repulsion. And that's known as a strong force. And neutrons also have the strong force. So neutrons kind of act like glue to put nuclei together. And you'll see this later on. Some of the heavier elements need more neutrons to have more of that strong force to keep the nucleus together. And when a nucleus is no longer stable, that is called radioactive. It is an unstable nucleus. And the neutron to charge ratio, the N to Z, it starts off as being more or less a linear function, the x equals y line, but after as the nuclei gets more massive, more neutrons are needed as well. And if the ratio is too high, neutrons are converted to protons via beta decay. If it's too low, then the alpha decay happens. So here is the line. As I mentioned, this chart here, you look at the number of neutrons on the y-axis and the atomic number on the x-axis, and you see the x equals y line there. As the elements get more massive, then the line creeps up. And of course, you can see that you have the stable nucleides there in the darker blue, and the yellow are the various different isotopes, but those are unstable. So magic numbers. So just like they're particularly stable formations in electrons, like noble gases, there are magic numbers also with nuclear events. And these are 2, 8, 20, 28, 50, 82, and 126. So we're looking for some of these very stable, super heavy elements. The most magic of the number is 28. So 28, 28, the iron 56 is the most stable nuclide. It is the most stable that there is. So anything with a charge a Z greater of 83 are radioactive. This is debatable. Bismuth might be radioactive, but maybe it's not, maybe it is. We're not entirely sure. But this is a maybe. But anyways, there's various pathways that the radioactive nuclei follow, and we know these as the decay series. So for instance, here's uranium-238, and it decays the thorium, and you can see the path that it takes, and one of the paths that it takes is to form radon, and eventually forms lead. So it keeps on going down, and then it forms lead. So much of the lead that's in the Earth right now has decayed from uranium-238. And how do you detect radioactivity? One of them is a dosimeter. So a dosimeter, this is something like it's something you wear, and it has salt crystals in them, and they the amount of light that you have here is proportional to radiation exposure. And quite frequently, they have film in here, and you develop the film to see how much has been what the exposure is from that film. So another one is a Geiger counter. So, Geiger-Muller counter, and you have a inert gas like argon inside the tube, and if there's ionizing radiation goes in, what happens is the argon is ionized, and then it's found in the detector, and then of course then you can hear the clicks is frequently with the Geiger-Muller counter. So oftentimes it's called a Geiger counter from that. And also have a scintillation counter. This is, you have a material, frequently something like cesium iodide is used, and then when a radiation hits that, it flashes, and then you look at the light. So many of the digital sort of radiation counters, these are oftentimes scintillation counters. So radioactive decay is first order kinetics. So and it's always, I think this is interesting. Almost every chemical reaction is first order. Many of the things like bank interest is first order, and also radioactive decay. And so, but with radioactive decay, it doesn't matter the temperature. It's just plain old kinetics. It's probability as well. So if you study radioactivity, it's not always consistent, and it's because it's based off of probability. But the probability over time follows first order kinetics. So it's interesting to follow. And since it's first order kinetics, the half-life is oftentimes used, and the half-life is just a natural log of 2 over the rate constant. And the smaller the half-life, the more radioactive the nuclide is, and the higher level of radioactivity, we call this hot. So the hotter something is, the more radioactive it is. And so here are some half-lives of various nuclides, and you can see here like a radon 220 is going to be pretty hot, where uranium and thorium are not particularly hot. And also you can see uranium and thorium, we have them around for quite some time. So you can have things they're radioactive and they're unstable, but they may not be all that radioactive. Oh, so you look even further, the thorium 219. Something to note, if you haven't noticed already, the odd numbers are very unstable. So for protons and neutrons, the odd numbers are the ones that are less stable. It's something called the pairing energy that happens when protons and neutrons are paired. You see in electrons too, but it's pretty negligible. Where protons and neutrons, the pairing energy is very large. So the half-life just follows the kinetics, and if the half-life is a minute, that means after a minute, half of the material is there and is gone, and you can see that the decay is the exponential decay here. So more at the radioactive decay. This is just the first order process, the first order integrated rate law, if you remember this, and this just follows that the activity at time t over the initial activity. And I'm using the activity because that's frequently what is used, because it's real easy to find the activity. It's just the reading that you get on your Geiger counter when you're doing this, and it's real easy to find radiation. That's one thing that's nice about radiation. It's real easy to work with this stuff. It's really easy to find. It's really easy to do calculations with it. Radiocarbon dating, also known as carbon dating. The half-life of carbon is carbon 14 is 5,730 years, and carbon 14 comes from nitrogen, and with oxygen. Oxygen in the sun, So, well, this action on the Earth and then radiation from the sun creates carbon-14. And it's made at about the same rate. This, of course, has changed a bit, though, because of nuclear power and atmospheric nuclear testing. We blew up about 500 nuclear weapons in the atmosphere, and that has shifted the amount of carbon-14. Carbon-14 is a little higher today than it was. So we anthropogenically, we as humans have generated more carbon-14. But so carbon dating is not going to work so well for us. Uh, Actually, we would come as, for me, I would be seen as older than my parents, because my parents were around when the closer to when the, well, I guess they were around with the nuclear testing. So they're going to be more, they're hotter than I am, they're more radioactive than I am. So carbon-14 is not going to work so well for us right now. But and we can still, if there are things before the 1940s, it works quite well. And generally speaking, the living carbon-14 to carbon-12 is more or less constant. But then, well, then after the creature dies or is turned into something else, right? So if tree turns into paper, well, the tree has stopped to collecting carbon dioxide to make photosynthesis. Therefore, the carbon just starts to decay, and then you can look at the activity of the carbon, how much carbon is there versus fresh carbon, and then that tells you approximately how long the creature has been dead. And there is a limit to this, though. It doesn't work past 500,000 or 50,000 years, and it's hard because of just detection limits. And of course, this is there's some error in this because it's probability, but it works pretty well. It's a decent range. So what about for other things that are more than 50,000 years old? You can use other things. The ratio of uranium-238 to lead-206. So that tells you about rocks. Also, potassium is another one you can use for that. So it'll tell you how long material has been since a supernova, basically the original amount of uranium that has come from the material forming. And from this we tell the age of the Earth, and we look at both uranium and potassium-40, and and the Earth then is around 4.6-ish billion years old. And it says it's inconsistent. That's not true. The estimated age of the Earth is consistent with the age of the universe, which is around 14 billion years old. And that's from the background radiation. It's a combination of the background radiation and the Hubble's law, the expansion law. So this side's wrong. So nuclear fission, nuclear fusion. So fission is to break apart. Fusion is to stick together. And so large nucleus splits in two, that's nuclear fission. And fusion is smaller ones formed together to form a heavier elements. So depends on where you're at. Fission and fusion release energy, and which one is more exothermic? It's going to be fusion. Fusion is much more exothermic, generally speaking. So, for instance, here's uranium-235. So remember that odd number. It adds the neutron. When uranium-235 gets a neutron, so this one has to also be known as a slow neutron, or also known as a thermal neutron. And those slow neutrons then are absorbed by the uranium-235. It releases the pairing energy, and that greatly excites the energy of the nucleus. So the energy of the nucleus goes up, and then the nucleus actually splits in two. So it's not an even split. It splits into two. And there's a wide range of products. It's not just going to be barium and krypton. There's various pathways that it can go down. There's a bunch of different products. But it splits apart. and then also releases more neutrons, and then those neutrons can then go and split other nuclei. So it depends on the neutron. If it's a fast neutron, those tend not to cause fission. But there are certain cases that can cause fission. So for some nuclear weapons, they coat the nuclear weapon in uranium-238 and depleted uranium, and the really fast neutrons can actually fizz those. It can break them apart. So, but it's just the fast neutrons can just plow into it and just rip it apart that way. So, it can be slow or fast, depends on the circumstance for nuclear fission. But generally speaking, it's preferred to be slower. And the only exception for that is when you have the really fast high energy neutrons. And the only way you're gonna get those really fast high energy neutrons is in an atomic weapon or like a star kind of thing. But it's gonna come from a nuclear fusion reaction for those. And when you try and control these nuclear reactions, you need to have something to slow down those neutrons as well, and that's something called a moderator. And we'll talk about that when we talk about nuclear power. So for fissionable material, it's the odd number. Remember the odd number, and it's less than 1%. It's 0.7%, depending on where you get the uranium. There's something called the Oklo reactor, and there was a natural nuclear reactor that and they found that the uranium was even more depleted in uranium-235, but that's because there was a natural nuclear reactor. Is the uranium-238. This is a mistake. Uranium-238 is the most abundant isotope. It's non-fissionable for thermal neutrons. You can get for very fast neutrons, it'll be fissionable, but that only happens in very unique circumstances like atomic weapons. In order to produce a fissionable material, you have to enrich the uranium-235. Well, it's mostly true. You can, if you have a heavy water reactor, the heavy water will moderate the neutrons enough that it'll work. But most nuclear reactors are known as light water, or it's got hydrogen instead of deuterium. So you can get it to work with uranium from the ground, but you have to use deuterium, which is harder to find. So chain reaction, this is just keeps on going. The neutrons produced from the nuclear fission then go and go on and keep on going, keep the reaction going. But it takes quite a bit to get it to work. The critical mass, this is more for explosions, for nuclear explosions. The critical mass, it depends on, talking about, for uranium, it's about 50 kilograms. You need about 50 kilograms of uranium critical, it depends. For a nuclear reactor, you can do it with much less. But for an atomic weapon, you need about 50 kilograms. And here's the chain reaction. You notice it's not always going to be the same product. It's different products. But I guess for simplicity's sake, we're just putting there. Nuclear power, we get about 1/5 of the electricity in the United States for nuclear power. Depends on the country. Some of the countries get really, really high. Most of the nuclear reactors will either have pressurized water reactors. Some of them are boiling water reactors. One of the problems we have with nuclear power is that it uses saturated steam. It doesn't use superheated steam, so that it's not as efficient. So the efficiency in nuclear power plants are actually kind of low. But part of it is we don't like to run our nuclear power plants very hot. So we like to keep them kind of cool. Actually, the temperature of a nuclear reactor is less than that of a candle flame. So we really keep them kind of low in intensity in this country. But that's reasonable because it's safer. So here's a nuclear reactor, and you have the nuclear core, and you have the fuel rods there. It's just a pile. It's kind of like, imagine a bunch of hockey pucks. Imagine a bunch of hockey pucks, and they're usually, it's lead, uranium oxide with a coating. Oftentimes it's niobium. And then you have the control rods. These are various materials. Depends on which material you use. What the control rods do is they absorb neutrons. and in the off state, the control rods are all the way in. And then there's the moderating material. Most of the nuclear power plants that we have use water and specifically light water to do it to as a moderating material. You can use other materials like liquid sodium is also frequently used. It's probably actually liquid sodium is a safer one than water. But this is also known as a pressurized water reactor because you have the pressurized water then goes and generates steam from another source. And you can also have boiling water reactors. Another one, the nuclear core just boils water, and the steam is then pushed on the turbines. So, when something happens, you turn the reactor off by putting the control rods down. The problem with this is that even though there's no nuclear reaction, this happened in Fukushima. The core is still radioactive, and radioactive, it's hot. It generates heat, and if it's sealed in, eventually the pressure builds up, and it built up to the point where actually the heat built up so that water was cracked into hydrogen and helium, and that ignited, and that caused the explosion at Fukushima, for instance. And it was just from the radiation there. Just eventually, with thermal energy, caused a chemical reaction. So it wasn't a nuclear reaction, but it was a chemical reaction that caused the plant did melt down. But the meltdown means the fuel rods they melted, and it was a partial meltdown. Versus Chernobyl. Chernobyl was a huge disaster. Chernobyl was far, far worse than Fukushima. They list them together, but Fukushima is not nearly as bad as Chernobyl. So let's look at nuclear versus coal. So 50 kilograms of fuel, you can make electricity for 1 million people. It's no air pollution, not entirely true because you still have to mine the uranium and you have to ship it. So there is some air pollution if you look at the entire cycle. Coal burning, though, produces much, much more emissions than that. But nuclear looks pretty attractive in this regards. So the core, though, they have the fuel rods subcritical. It means that it's not going to detonate. So you need to have very heavily enriched uranium to cause a nuclear detonation. And nuclear power plants in the United States, they're usually enriched to about 3 to 9% uranium-235, and from the ground it's about 0.7%. So you can't get to a nuclear weapon from that. And the control rods, so boron, cadmium, there's various other things you can use, and these absorb the neutrons. And the rods placed in the moderator, use them to slow down the neutrons and make them thermal neutrons. And water is a very common moderator. Liquid sodium, as I mentioned before, is another one. And then nuclear reaction happens and generates heat, which then generates electricity. If you want to see something horrifying, you can look at the picture of the first nuclear reactor. It was in the basement of the University of Chicago. They just had just sitting there out in the open, and it was pretty hot in there, and the guys were there working with their shirts off. So yeah, that was not exactly we didn't know what we were doing, so we didn't realize how dangerous the radiation was. So here's the core and then the fuel rods, and this is for a pressurized water reactor, and then depending on how hot you want to go with the reactor, you have the fuel rods up or down. If there's ever an issue, the fuel rods are supposed to go straight down and turn the reactor off. So problem with nuclear power, I mentioned Chernobyl and Fukushima, and Chernobyl was the worst nuclear accident ever. Some of the nuclear waste, though, it's really highly radioactive. It's like when the stuff comes out of the core, it's very radioactive, and it's hot. It's radioactive for quite some time. And then after after it decays a little bit, the higher energy decay. There are some things that stick around for a while. So plutonium that's formed will stick around for tens of thousands of years, and strontium 90, cesium 130. It's cesium 137. Those are all they have about a half life. They both have a half life of about 30 years. They stick around for a couple hundred years. So then, what do we do with this radioactive waste? And we thought about putting it in Yucca Mountain in Nevada, and the idea with that is the groundwater was moving. Part of the problem that you can put them into a steel bin, but the steel bin lasts about 50 years, and if you have radiation that sticks around for a couple hundred years, in the case of strontium and cesium, and then what about plutonium that can stick around for tens of thousands of years? Well, that's a problem. And so you want somewhere where it doesn't rain, and that's one of the reasons why I'm looking at Yucca Mountain. There's other ways to store them. You can just put a huge amount of electrical current through it and form kind of a glassy substance. That's one way to store really high energy waste. So we're trying to figure this out. This is something that's an ongoing problem for us with nuclear power. And okay, so let's talk about the energy from nuclear fission. Where does it come from? It comes from matter turning into energy. And maybe you've seen the equation equals mc squared, where E is energy, m is mass, and c is the speed of light squared, so c is squared. And that means a little bit of matter can turn into a lot of energy. So a mole of uranium-235 that fizzes forms that much energy. And later on, you'll see some other conflicting numbers. That's because the neutron is included in that. So that's just the uranium. To give you an example, a very exothermic chemical reaction produces 1 million joules per mole, and we're looking at 10 to the 13 joules per mole. So 10 to the 7th. So 10 million times more than a chemical reaction. So that's the reason why nuclear reactions are looked at like, wow, that's a lot of energy. So the energy comes from mass defect. So meaning the amount of matter after a nuclear reaction, assuming it's exothermic, is less. And you can have endothermic nuclear reactions, of course. That's how many of the elements form. It's how the elements have formed, or in endothermic nuclear reactions. So, but the exothermic ones, the energy is released. And the energy that's released when a nucleus is formed, this is known as the binding energy. And this MeV is mega electron volts. An electron volt is that's the energy of an electron. In an electronic field, so the 1.6 times 10 to the minus 19 coulombs is a charge of an electron, and in the 1 unit electron field, so an electron volt is 1.6 times 10 to the minus 19 joules. And so that mega electron volt is just 1 million of those. And 1 atomic mass unit of mass defect is 931.5 mega electron volts. The AMU, this is based off of carbon-12 right now as I'm recording this video. This may change to silicon in the future, who knows? But as I'm recording this, it's carbon-12. Carbon-12 has 12 atomic mass units. So, and generally speaking, the greater the binding energy, the more stable the nucleus. The most stable nucleus, of course, is iron 56. So if you look at this nuclear reaction here, and then of course uranium depends. There's different reactions. Okay, so it's different reactions, and it depends on which one. For this specific one, the energy produced is the mass loss. You can see here it loses a little bit of mass, and then that turns into that much energy. It doesn't look that impressive there, but then you multiply it by Avogadro's number, 10 to the 23rd. It's a bit more impressive. So then you have there. So And okay, so here's curve of the binding energy. The y-axis shows the binding energy, and the x-axis is the mass number. And you can see that there's actually a spike there with helium-4. And then iron 56 is the top of it. Iron 56 is the most stable nucleus there is. And this is the reason why you have supernova, actually. So in supernovas, so it's a specific type called a type 2A supernova. When you have enough iron 56 forms in the core of a star, then iron 56 fusion is then endothermic, which causes the core of the star to shrink because it's a gas. Because you cool off a gas, it shrinks, which causes more pressure, which causes more fusion. And then the star's core collapses. And that causes a shock wave that lights up the star and has a huge amount of nuclear reactions. That's how many of these heavier elements are formed in these nuclear reactions from the supernova. And the Earth itself has quite a bit of iron in it. Of course, it's in the core of the Earth. The core of the Earth is somewhere between 100 and 80% iron. It's believed to be closer to 80%. It's nickel iron. We believe it's about 80-ish% iron. Of course, we don't know because we haven't been there, but we believe that's what it is. And so the Earth itself has quite a bit of iron, and that's from. We also believe that the sun is a third generation star, meaning that the Big Bang happened, and then that generated a star, that one nova generated another star, that one nova, and then that material formed the sun. So we believe that we're at least the third generation from the birth of the universe as far as stellar formation and our planetary system. But you can see to the left of iron, generally speaking, fusion is exothermic, and to the right of iron, fission is exothermic. That doesn't mean that you can't have fission, or you can't have fission on the left of iron, or you can't have fusion on the right of iron. You can still have those. They're just more difficult. And certain nuclides are also better at things. Xenon, for instance, xenon's very good at nuclear fusion. And I can see xenon is actually, of course, heavier than iron. It has something called a barn size. The barn of xenon is pretty big. It's really easy to get the nucleus to react. So nuclear fusion, you combine them together, and this is where stars get most of their energy from, including the sun. The sun right now is primarily turning hydrogen into helium, mostly via a process called the CNO cycle, where the carbon-12 actually turns into oxygen-18 and then has an alpha decay back down. So it's a nuclear catalyst of sorts. Also used for hydrogen bombs. So although bombs these days, they tend to have more lithium deuteride in them than straight tritium. Hydrogen bombs are also known as thermonuclear bombs. That's because you have a fission nuclear bomb provides the energy, the activation energy for the fusion reaction, hence the name thermonuclear. So hydrogen bombs there. And the fusion bombs generate much more energy. And so if you have a fusion bomb, if you have a thermonuclear bomb without a coating of uranium around it, that's also known as a neutron bomb. So maybe you've heard the term neutron bomb. If you put uranium-238 encapsulating the thermonuclear device, then you can get an even stronger yield. So the largest bomb that ever detonated was a Tsar bomb in Russia. So the Russians have huge nukes, bigger, at least 2 to 4 times bigger than we have in the United States, actually. So, but the United States gets by with more precision than we do with size, where the Russians were not as good with precision, so they got around that by just having bigger weapons. So I guess that makes sense, but kind of scary in a way. So here's fusion, and you can form the So in this case, tritium, deuterium react to form a high energy neutron. That's the neutron bomb. So if you can either capture that neutron by putting uranium outside the bomb, and then that gets more energy that way, or you can just or you can just let it rip, and then you have a neutron bomb, and it generates helium. So besides nuclear weapons, how can you do nuclear fusion? Here's a tokamak reactor. It's really hard to get these to work. I mean, you can get nuclear fusion, but right now they're very energy negative. So the energy you put into the system, you do not get back out. And we're trying to figure out how to use a tokamak to get to be energy positive, but we haven't gotten there yet. So other types of nuclear fusion, there's something called the National Ignition Facility that's in Livermore. They have little pellets that they shine with lasers, and then that causes nuclear fusion in those. So that's not listed in the textbook. The National Ignition Facility, though, that we've got that to work as well. But who knows if we'll eventually use that to make energy. Right now, we're just studying nuclear fusion using the ignition facility. And this one here, the tokamak, it's like I said, it's really, this is a really hard thing to do, to generate electricity from this. Well, I mean, it's easy to get electricity from heat, but we haven't got to the point where we can get a stable, long-lasting nuclear chain reaction and control it in a fashion that it's energy positive. Right now, it's energy negative with our current technology. So who knows in the future? It'd be really nice if we can figure out how to do this. Transmutation, this is when you transform one element to another. And you can use this, you can do this artificially to see what's in a sample. But this also happens naturally. So you can make, so that, for instance, Rutherford did this, and Irene Joliot Curie did this as well. And californium, for instance, can be made by bombarding uranium-238 with carbon-12. So why do we care about californium? Californium is an excellent neutron source. So californium frequently is used as the starter for nuclear weapons, actually. So if you're wondering why we're talking about californium is useful in that regards. And I already mentioned with artificial transmutation, you can use this you can bombard samples with neutrons and then look at the decay series that comes off to see what's in something. And you can do this in particle accelerator, either a linear accelerator or a cyclotron. So the cyclotron is it's the materials spin around and you accelerate them that way. Well, a linear accelerator is just a straight long shot. So here's a linear accelerator, and so one of the larger linear accelerators is known as SLAC. It's a Stanford Linear Accelerator. So that's a very, I believe that's an image of SLAC right there. And it's just a very long linear accelerator. Many other particle accelerators start off with linear accelerators, and then they can throw them into a particle accelerator. And they do different things. The different particle accelerators can do different things. Depends on what you're studying. So where I went to school, Berkeley, they have a synchrotron there. You would have a linear accelerator shot the electrons into the synchrotron, and then you would have an undulator. So imagine kind of like magnets, and the electrons would move around the magnets kind of like a sine wave, and as they bend, they would emit radiation, and then you would use the radiation to do things. The Stanford Linear Accelerator also emits radiation. It has a higher energy, so higher energy X-rays than the Berkeley Advanced Light Source synchrotron had. So both great apparatus. So if you ever get a chance to visit and/or do research with them, they're both very interesting apparati. But linear accelerator, in essence, like the old cathode ray television sets, is essentially, in principle, a linear accelerator as well. So if you want to look at a cathode ray. A cyclotron, so this, when you have the source, usually a proton, and then it spins around and it generates, it increases in energy, and it shoots out And Ernest Orlando Lawrence, he's the one that invented the cyclotron. Got a Nobel Prize for that. So the cyclotron there can be. Cyclotrons are very frequently used also for making super heavy elements. They can do nuclear fusion with elements heavier than iron. So we can do this here on Earth. And okay, let's talk about radiation effects it has on life. So there's acute, that's the immediate damage, and then there's a long term, the chronic. So cancer risk is more the chronic one, and some genetic effects that can also actually pass on a mutation going forward. So the acute effects, you can depends. It's just cell damage. It's just radiation doesn't give you superpowers. It just damages cells. So a sunburn is an acute radiation burn, and so it's just like similar to a thermal burn. It just damages cells, and it depends on what the source is. And if you get enough radiation damage, you can get radiation sickness. So, and these frequently happen. Well, it doesn't. Unfortunately, radiation sickness is a very rare thing, but it might result in death. So, they're over low periods of time, low doses over extended period of time. These might cause an increase in cancer. And what happens with cancer? A cancer cell is formed, and cancer cells are specific mutations, such that the DNA of the cell is altered, or in this case, it's damaged by radiation. If the DNA is incorrectly repaired by the body, then that can create a cancer cell. So then the cancer cell might be activated by something else, and then then that cancer region can grow abnormally. It can either be benign, which means it's growing slowly or not at all, or it can be malignant, which means it grows very quickly. And the malignant tumors can spread, and they can also just simply put pressure on the surrounding tissues. So if you have something like liver cancer or brain cancer, if the malignant tumors are there and it's putting mechanical pressure on the surrounding tissues, that can damage those tissues and cause them not to work as well. Also, the malignant tumors, they gather lots of nutrients. They can starve nutrients around the area. So that's the really quick version of how cancer works. So it's hard to tell with radiation, because there's just so many different causes of cancer. People, oh, you can cure cancer. Well, cancer is a lot of different types of cancer. There's many different causes. There's many different treatments. It's not like a one thing will get it all done. So that's one thing with cancer. And I'm using the words like might. I mean, does radiation cause cancer? Like, yes, it does. But the process, we know certain things, but it's hard. In many ways, it's hard to predict. It depends. And one of the causes of cancer, unfortunately, is bad luck. I mean, among other things. Of course, the working around radiation certainly does increase your risk of cancer. Or if you have an area that has more radiation, that certainly increases your risk of cancer. But it's a risk. It's a probability. So it doesn't mean it's going to happen. And then, of course, anything that causes a mutagenic radiation can cause a mutagenic effect because it alters the DNA. So there's other mutagens than radiation, and many of them are far worse than radiation. But we haven't quite seen this in humans, but the passing on of genetic defects. So measuring radiation exposure, there's a bunch of different ways. So the dose is the amount absorbed by the exposure is how many decay events. The dose is the amount. So Curie, for instance, is just the exposure of it. A Gray measures the amount that's absorbed by a body tissue, and the rad is just a function of the Gray. And how do you measure it? You can look at the relative biological effectiveness. So, frequently we use the term REM, the Roentgen equivalent man. And it's and the dose in rads times the RBE equals the dose in REMs. And rhodogen is that it's the radiation that produces a charge of, so remember, ionizing radiation creates a charge of 2.58 times 10 to the minus 4 coulombs per kilogram of air. So that's a rhodogen. And the dose, for instance, here, so you actually get some from an airplane ride because there's less atmosphere up there. So the radiation comes mostly from the sun. And of course, you get a higher dose of radiation during the daytime than at night. But you can get it from cosmic radiation. Terrestrial radiation, it also depends on where you're at. So, and I live in Hawaii, and we have very little terrestrial radiation here. And because of the rocks here, it doesn't have much uranium and thorium in the rocks, whereas other areas like the Midwest has much, much more terrestrial radiation. And we have natural radionuclides in the body, so carbon-14, potassium-40. These are emitters. So you yourself are slightly radioactive. Radon gas, of course, depends on where you live. Hawaii is not a big deal. Midwest, especially if you have a basement, you can get more there. Certain medical procedures, X-rays. X-rays are they're pretty low. Pretty low. A mammogram though has a bit more. Although CT scans, sometimes called CAT scans, these have a bit more. I had a CT scan and my dose was 1,700 millirem, so 1.7 rem. You're allowed, humans, United States, we say we have 5 rem per year. Oh, we'll talk about that later. I'll get to that in a second. But other things, building materials, this comes from the amount of uranium and thorium in the concrete. Concrete tends to have a little bit more of it. And luminous watches, you don't want them. You really don't want them. The tritium, promethium, no, you don't want them at all, to be honest with you. So in tobacco products, there's another one. You can get 16 rem per year from cigarette smoke. So be very careful if you are a smoker. There's quite a bit of radiation exposure from that. So we are allowed, at least in the United States, normal people are allowed to have 5 rem per year. If you take a class, you can get 10 rem per year. Like you gotta be careful. Now you can have 10 rem per year. You really don't see any effects of radiation until you reach about 20 rem, and that's when you have your blood is slightly affected. So the individuals in the Fukushima plant, they got a dose of about 25 rem. The workers there, so they're in the lower threshold. I mean, not to say they're not brave, but if you're wondering, the Fukushima workers were on the order of about 25 rem per year, and above, so about 60 rem. That's when your hair can start to fall out. So it depends on the person, but around 60 rem, that's when the hair falls out. 100 rem though, you're going to get radiation sickness. It's going to, especially your stomach, you can get skin lesions and it affects your lining of your stomach and various things. It's I've never had it, of course, but it's apparently it's like having a bad case of the flu is what radiation sickness feels like. It depends on the person, depends on the exposure and the time, and of course, really short, intense periods. Those cause quite a bit of different damage. And it's just damage. It's just damage to the area. So kind of like a thermal burn is just thermal damage, and the same thing with the radiation. It's just you're getting attacked on your cells on a molecular level, and it causes intense cell damage. And is your body able to repair that cell damage? And if your body is able to repair that cell damage and you survive, then that's great. If you are unable to repair that damage, or if the damage is repaired incorrectly, then you get cancer. So it just depends what happens to the patient. and higher dose, of course, death and can happen quickly. But that's the scary part. There are some good things that we can do with radiation. You can use radio tracers, and we do it quite a bit in the human body. So medicine is good with that. We can also do it for research. You can use isotopes, and you can look at chemical reactions and seeing where things are with the different nuclides. You can also do it to track flow. So let's say you have a natural gas pipeline, you have a leak somewhere in the natural gas pipeline. So what you do, you can release a little bit of radioactive material, and then you can fly along it with a helicopter, and you can look to see, like, oh, where is the radiation? And then suddenly, oh, the radiation stopped, and you have a pretty good idea where the leak is, for instance. So you can do radiation that's for leak tracing, but we also do it in the human body. So here's a bone scan. Bone scan uses technetium-99, and that is made from molybdenum, and it's a metastable. It just releases gamma. It's an unstable nucleus. Has a half-life of 6 hours, and if you see here in the image, it's pretty bright around the bladder because your body tries to excrete it. So. And you can see this looks like a pretty healthy patient. I'm not good at reading them, but this usually, if there's an injury, maybe a little bit in the upper back, in the thoracic region, there's a bit of activity, or maybe around the hips, maybe there's something there. But this patient, all in all, looks pretty healthy at first glance. You can see the large amount of activity there around the bladder, but that's normal. So common radio tracers, so technetium-99 metastable. And then this is for the bone scans. Iodine-131. So this is used for the thyroid. It can also be used to kill the thyroid for things like Hashimoto's or Graves' disease. Iron-59, look at the imaging in the blood. And thallium-201, so for your heart. Fluorine-18 for PET scans, so frequently used in the brain. Phosphorus-32, just look for various tumors. And so, for instance, here a PET scan, and you can look for glucose, and then to see where activity is in the brain, where the glucose is taken in, or where it's not. So both those are important information for the brain studies. Also, radiotherapy. Cancer cells are more sensitive to radiation. The cells will divide very quickly. So in the human body, the cells that divide very quickly are hair follicles and stomach lining. So those are very sensitive to radiation on the human body. So that's the reason why radiation sickness, your hair falls out, and you usually get stomach issues, is because of the damage to those cells. But cancer cells, they also divide very quickly, and so because of that, they're just more sensitive to radiation and also chemotherapy as well. Same thing with humans and chemotherapy. What happens to humans and chemotherapy? Hair falls out and stomach issues. So same thing with radiation. And so it happens. It's the high metabolism cells. And here shows in gamma ray treatment. We're doing an exploration of other things than just gamma rays. So, and the nice thing about gamma rays, we can also target. We can hit multiple beams and hit tumors and damaging that. And the idea then, if you damage the tumors, then hopefully the immune system can then clear that cancer. Your immune system will clear out cancer. So it's not like we're completely vulnerable to cancer. The human immune system, any animal immune system will get rid of cancer. But this is just to help the immune system along the way to flush it out. So what else can we use radioactive isotopes for? Americium-241, that's used in smoke detectors. So the smoke detector works by ionizing. So if you have smoke go through a radioactive beam, and then it ionizes the smoke, and they have a detector, and then it detects that. You can have insect control. You can sterilize a bunch of males and then release them, and the males will mate and then will produce no offspring. Food preservation, so radiating food can prevent certain things. I can see these strawberries on the picture on the right. They have irradiated and non-radiated. The non-radiated have the mold growing on them, so the radiated can kill much of the things that would spoil the food. So radioactive tracers, you can do this just for research. We do this in research as well. I already mentioned for flow analysis and chemical analysis. This is a way to study what's in something. You can do an elemental analysis using neutron bombardments, but there's other ways. So you can, for instance, you can use atomic absorption. So there's other ways to do it. Atomic absorption is very frequently used. The activation analysis is not as frequently used for that. And thank you for listening. Hope you enjoyed today's lecture.